Hello everyone. Today I'd like to revisit loop pipelining in HLS, which has been widely used in most HLS applications. HLS tools today can do a lot of powerful things, such as automatically pipelining loops. This is super useful for software engineers to build hardware accelerators. This talk mainly asks a question that, can a state-of-the-art HLS tools always find the loop pipelining solution for best performance? If not, what are missed and why is that? To get started, let me briefly introduce loop pipelining in HLS. Like software pipelining, loop pipelining parallelizes loop iterations in hardware. The initiation interval, also known as II, is defined as the number of clock cycles between the start times of the same operation in two consecutive loop iterations. I is usually used to evaluate the performance of the loop. A smaller II results in a higher throughput. HLS tools like Can Vitis HLS automatically searches for the minimum II for the best performance by default. Here we take Vitis HLS for example. The loop on the left that has an if condition is to be pipelined. The content of the code is not important, and I will explain it later. Interestingly, we found that when we try to pipeline the loop, the minimum II found by Vitis HLS is 41. However, if we force to pipeline this loop with an II of 2, the results are still correct. Well, this is very interesting. 41 and 2. That's a big difference in performance. Why can't Vitis HLS find it? What are we missing? To further explore this, let's revisit the formulation of traditional loop pipelining in HLS. Let's start with a simple example. The loop on the left accumulates a constant on a variable named s. Because the accumulation operation requires the result from its last iteration, the dependence distance is 1. The II is restricted by the latency of the floating point adder, so we have a minimum II of 4. The pipeline loop schedule then looks like that. Here is another example. Instead of accumulating data on a variable, here we update a vector named a. The dependence distance is then 3, as the result of the first iteration is only required by the fourth iteration. The latency of line 2 is 7 cycles. This results in a minimum II of 3. So by having a larger dependence distance, more iterations can be parallelized. In summary, there are two constraints that affect loop II. The iterational latency, which is the number of clock cycles between the start times of an operation and its dependence, and the dependence distance, which is the number of iterations that separate an operation from its dependence. A larger iteration latency can cause a larger minimum II, and a larger dependence distance can cause a smaller minimum II. The previous two loops are simple examples. How about complex loops? In the motivating example, we find there are two dependencies in the loop. A dependence between line 2 and line 4, and another dependence between line 2 and line 8. Well, a general loop could have more than one dependencies, and each dependence has an iteration latency and a dependence distance. Existing approaches like SDC-based scheduling approximate these two terms independently. It takes the maximum value among all the iteration latencies and the minimum value among all the dependence distance to determine the minimum II. However, such approximation ignores the correlation between the iteration latency and dependence distance. That is, the minimum dependence distance may not be reachable when the iteration latency is the maximum value, which means that we could have a smaller II than the approximate II. Our work captures this and improves the hardware designs to have better performance. As a solution, we propose a new scheduling formulation that includes the correlation between these two constraints. This formulation can capture the corner cases that are ignored by the existing SDC-based scheduling model. We use SMT-based approach, so our tool can also analyze dependencies among nonlinear memory access. Taking Vitis HLS for prototyping, we present our work as a fully automated HLS path. Our tool can also be extended to support other HLS tools. Now let's go back to the motivating example. The first dependence has an iteration latency of 82 cycles and a dependence distance of 63. The second dependence has an iteration latency of 8 cycles and a dependence distance of 9. In this case, the maximum iteration latency and the minimum dependence distance cannot be both reached. The original formulation restricts the minimum II to no less than 10, while our tool captures that the optimal II is 2. Vitis HLS cannot figure out the nonlinear memory access at line 8, so it got even worse with an II41. We tried our approach on 4 benchmarks and compared II automatically determined by Vitis HLS. All the benchmarks lie in the 4th quadrant. This means that our tool achieves better performance and a larger area than Vitis HLS. On average, our tool achieves 11 times speedup with doubled area. Thanks. Our tool has been open sourced. If you are interested in this work, you can find the links of the paper and the tool in the QR code. And please feel free to come and talk to us.